All right, cool. So for this one, I'm going to go quickly over the ambient light sensor, because this is a sensor that lets you detect the amount of light that's coming into it. So what is it? It's essentially a sensor that it's a more advanced photoresistor is essentially what it is. The way it works is if it gets more light onto it, it changes the resistance of the components on the inside. And based on the change in resistance, you can use that for your logic and use that for your code to get different voltages in. So if you've got a really bright light shining on it, and that might make the resistor more resistance, you might get less voltage, and you might get a pin to trigger a low state, or you might get it to trigger a high state. So you would definitely use them in scenarios where light is very, very important. Maybe you're using it for a sensor that makes lights turn on automatically at night. You know how street lights will turn on automatically. I think they actually sync with the sundown times, but you could make a lamp that turns on when it gets dark and things like that. So essentially it's a photoresistor. So the resistance increases as the light intensity increases. So if I get a laser and I shine that thing straight into the photoresistor, then it's going to give me a really, really high resistance. Now, a really high resistance, if I've got that in a circuit, it will drop my voltage by a lot, as we saw in our earlier tutes. And it will trigger, like a digital pin can probably go to low, or some analog pin can probably give you a very low number, which means that you can go, oh, cool, in the program, if I read a low number of my sensor, then that means it's dark. And that's the way that sort of the logic carries through. And then obviously vice versa, if the light intensity goes down, then you get less resistance. And that's the real core of like what is actually going on with the sensor. So yeah, exactly, with something like vehicles, or like, you know, you've got street lamps, you might have a light resistor, a photoresistor in there to check for the outside and to see how much light is in the area. It's a good way to check. So this thing has to have a data sheet. So unfortunately for this one, the data sheet is mostly in Chinese, which is great, and a fun problem you run into sometimes. But it's still a good sensor. The voltage supply is about 3.3 to 5 volts. So you can hook this up to the exact same power rail as your Arduino. It will easily accept your 5 volts just fine, as you should be powering your Arduino at 5 volts at this point. And yeah, illumination range 1 lux to 6,000 lux. Have to check about exactly how much light that is, but yeah, and it responds pretty quickly. The main thing as well to remember is that it is actually analog. So we've been using digital pins up to this point and PWM pins, but the interface is analog. So on your Arduino, you've got A0 to A6, those pins, and you have to actually go analog read rather than digital read, and you'll get a number back from 0 to 255 rather than like high or low. But that's fine. So with the sensor, we've got the wires, and so the 3 wires connect to different things. So if we've got green, you can maybe put that to A0, and you've got a 5 volts, and ground is the gray one, which is the main way that sort of it's laid out. And yeah, so this is the main code that it's just for reading a value off of it. So you've got your void set up, and for us to be able to read data or read information off of our sensor, we have to do serial.begin, because serial.begin opens a serial port and it sets the baud rate to 9600, which is the baud rate of the Arduino. The essential way that it goes is when you have to initialize serial communication. It does not on by default. And so when you set it to 9600, you can actually see the data and read the data straight off the sensors if you make it print. So the reason that we start our serial communication up here is because we want to print our value down here. And again, we use that serial handle to do that. So we've got value analog read 0. So that's 0 relating back to our A0 pin. and because it's analog read, it will recognize that we're doing an analog pin. So it connects the grayscale sensor to analog 0, just reading off how much light it's receiving. And then all we're doing here is just printing the value of the value to the serial console. And I believe this handle may say it's in decimals or something like that. And then we get a small delay. So you can have a play with something like this. I'm sure that there might be an example in the Arduino file, but there might not be. Analog, yeah. Sometimes there could be, there might be something you can find online as well. But the basic program is something along these lines, where you might be doing a bit of a setup and reading the value off of it. And then you can use that value later in your code. Communication. Ooh, there might be an example. So is it in file examples communication? Did you say? This one? So, okay, yeah, cool. So there's a cool one. And it echoes and it goes for another port for serial communication. But yeah. Cool. So that's the main thing about our light sensor, is if you want to detect a bit of light or maybe trigger something, control something with light, that's there for you to use. The other one, if I can just, so let's cover the ultrasonic sensor as well, because this is probably one that a lot of you want to use if you can. So the main way that the ultrasonic sensor works is actually using echolocation. It's using a sensor that a lot of animals already have, and we just stole the idea from them. We've got bats and dolphins are the most famous examples. Submarines use this all the time. It is sends out a sound wave, and it times the amount of time it takes for that sound wave to come back. Because the speed of sound is constant in air, it can actually, and it's constant in any given medium, just different values. It will, you'll be able to work out with a little bit of simple math what the distance is between two objects. So that's exactly the way echolocation works. It's the way that animals can work out distance as well. So you've got 4 pins on the ultrasonic sensor. You've got your VCC, your trigger, your echo, and your ground. So you need 2 signal pins for the ultrasonic sensor. One is to trigger that you send a sound pulse, and the other one is echo, I think, to receive it, and you read off them differently. So for the next coding suggestion, this is the wiring that we've used, I believe. So yeah, we know the speed of sound is about 340 meters a second, roughly. And so it's about 34 centimeters per microsecond, which is what our microcontroller is going to be working off of. So time, distance, of speed, that means that just using some of the basic physics stuff, we can go, the distance is the time times this. Now, the reason we divide by 2 is actually because that sound wave has traveled out and then it's come back. So we have to divide by 2 to get the distance on the over the one-way trip. So we send a 10 microsecond pulse to the trigger pin to tell the sensor to send an ultrasonic pulse. So the trigger pin triggers a sound wave and it sends it out. And then we read off the echo pin how long it's taken for that sound wave to come back. So I believe it's the difference between your trigger and echo pin that you decide is the time difference. So they read the echo pins and measure the time difference proportional to how long the echo pin is high for. Yes. So the echo pin will stay high for a certain amount based on how long it took for that signal to get back. And then you convert it using the formula and you repeat the process over and over again. It's on a 10 microsecond pulse, so it does not take very long. It's very, very fast. It's doing what it's doing. So this is the start of the setup. Define the pin numbers again like before. We use trigger pin 2 and 4. Note that these are not necessarily PWM pins, I believe. I don't know if you need PWM for this actually. But yeah, you can define those pins and it will be fine. So we actually make long variables because we need to actually store quite a bit of data. And we get the duration and the distance. And then we set the trigger pin to an output, because our trigger pin is the signal that goes out to the sensor, and it tells the sensor to send a 10 microsecond pulse. And then we've got our echo pin, which is the pin that receives that data from the sensor and stays on for a certain amount of time, deciding our distance. And then we begin serial communication so that we can display our numbers in our serial console and we can actually see what's going on. So that's sort of your setup and your start of it. You've got your main loop here. You've got a send pulse. So all it does is it sends that 10 microsecond pulse, and then it gets the echo duration. So the duration is exactly proportional to how long it took for that wave to get back. So that means that our distance is microseconds to centimeters of duration, and then you get that. So yeah, echo duration to distance in centimeters. I believe they have to do the math for that. But yes, so functions used in the main loop, right? So we've done it separately. We send a pulse. So to send a pulse, we write the trigger pin to low, because then we clear it. So we make sure that it's low from the start, because otherwise we might get noise and it might already be on, and then we're trying to turn it on again while it's already on, and we might create issues. So we clear any of the previous states, and then we send a microsecond duration long pulse. So we set it to high, and then this US duration variable is the specified duration in microseconds. We've been doing 10 because that's what the sensor expects. And then our digital write pin back to low. So we want to turn it on for 10 microseconds manually. And we've done that in a function. And then get echo duration is the pulse in. So it's a function that's used within the IDE, and it lets you time for measure how long the echo pin is high for, conversion from echo. So yeah, this is the way that we've set it out in one of our solutions. However, you do actually in the Arduino IDE, if you go examples, there is an ultrasonic sensor one, I believe. Sensors, no, hold on. There definitely is ultrasonic, at least somewhere. But yeah, that's the main other way that I would recommend doing it. There's lots of information online on how to do it as well. So I might leave it with this for now then. If you want to see this again, let me know. I might actually put these somewhere. But yeah, it's the main way that you control them is by doing the math with the duration of the sound. So yeah, what I might do is, do people want me to cover the motor stuff now or wait for a little while? Now, motor and motor driver? Cool, let's do it. So we just get through it. Because that's probably something that people have been waiting for as well. Please let me do this. Motor. So let's launch straight into some of the motor stuff then and make this one a little bit longer. So introducing the MDD3A. This is the motor driver that we are using for the hackathon, and it's the main one that we've got available. The data sheet for this guy is actually really good. It's got a lot of the graphics in there, and the slides are pretty much made straight from it. So this is essentially the middleman between your battery voltage and the signals coming from the Arduino. So on the right side here, we've got the input signal and 5-volt output. So I believe that should say 5-volt input or output, but this is where we power the board itself. So the actual H bridges and the actual components that are on this board are powered on the right side. And then you've got your M1A, M1B, M2A, M2B. These are sometimes labeled as PWM signals 1 to 4. It's the exact same concept. These two at the top relate to these two at the top, and these two at the bottom relate to these two at the bottom. And then you've got your power input. So all you need to do when you've got your battery is we want to put our battery in the middle here. We want to go VB plus and VB minus. So you've got your red wire and your positive, and your black wire and your negative. And then that gives the power to the board to then manage it and do stuff with it. Based on the signals you send to it over the right, which are have to be PWM signals, it decides the polarity, so the direction of your motors, as well as the speeds of your motors at the same time. So you give both of those pins a signal. We need this board because the Arduino is not able to handle as much power as the battery is going to give it. It's a much more sensitive piece of equipment, and the motors need a lot more power to be able to run. It acts as a double H bridge for those of you interested. It essentially lets you, it's kind of a set of switches in the shape of a H that let you change the direction of how you're going. And yeah, it's got a really good breakdown of all the components on the data sheet. So as for actually using that, here again, we've got that PWM 1 to 4, but it's the exact same as those M1A, M1B. It's just labeled slightly differently. So don't get caught off guard with that. But the essential idea is that you've got a bit of a truth table as well. You need to give it 4 signals, and it needs to have 4 signals written to it every time. And the idea is that if you match the 2 power levels, so if you set PWM 1 and 2 to high, well, what that's going to do is the scenario on the bottom, where all of your inputs are high for a motor. So both of your outputs are going to be high, and it's going to match the voltage and the PWM signal at both ends of the motor, which is going to get it to break. It's going to get it to stop, right? What you want, if you are trying to move, is to have have it going one direction and in the other way. So setting one of those PWM signals to a high and setting the other one to low will allow it to spin in a certain direction. And whichever way you do that depends whether you go forwards or backwards. So if you alternate these, you got a movement going. So yeah, if you were to put that one high and PWM 1 to high, PWM 2 to low, then motors A would spin forwards. So essentially, if I put this one to high and this one to low on M1A and M1B, then motor 1 or motor A would spin forwards, is what I'm trying to get at. It's a bit interesting, but yeah. However, this motor driver is great because it actually comes with its own fun little Arduino library. So another fun skill that's good to know when you are doing a lot of stuff with Arduinos is that the Arduino IDE is incredibly widely supported, and lots of companies have created libraries for you to be able to work with. And the Arduino IDE is quite good at actually managing these libraries and containing them. So the way that you go is you can manage libraries and you can install it. So I'm pretty sure most of you are hooked up to EDU Roam at this point and have some kind of internet. But if I go to File and I go to, or is it Sketch? Yeah. So you've got Include Library, and then you've got your Manage Libraries. And this is a great piece of the Arduino IDE, and one of the best things about it is how seamless this is. So the company that has made this motor driver is called Citron. And so if you search in here Citron motor drivers library, it will come up with its own motor drivers library. So all I'm going to do is so that it's Citron motor driver libraries. And it's pretty much got it all built in for you rather than having to go through the pain. That is exactly what I typed. Citron motor drivers library. I already have it installed too. Can it come up? Thank you. So yeah, Citron motor drivers library. If you install this one, it usually is very, very quick. And so now you've got that. Now, the beauty of this library in particular is that it actually comes with examples. So if you go into your example section, you'll have down the bottom, it'll say examples from custom libraries. And the beauty of it is that you've got the Citron motor drivers library examples right here. and you can go into, I would suggest doing the PWM dual, because it's using both the motors. And then there you go. You have a test script that explains exactly what pins that they have hooked up to what motor inputs. It explains exactly who made it. You've got more extra information. It includes the library for you, and it's got all the different pins. So I recommend, especially reading through this, is really, really good. And it's got the exact motor setup that they've used to stop or start the motors in the way that they've set it up. So this is a very valuable file to look at and essentially literally steal from, because you can just take what they've done rather than having to create it yourself. And it's quite nice. So yeah, that's the main way I would get started with the motor drivers. Now, servos are fun. They are, you can control them a little bit more in a custom way. So the servos can go between -90 and 90 degrees. It does depend a little bit on how the servo is set up. I believe the one that we're using is 0 to 180. Yeah, so for us, we give it the signal 0 to 180. The angle is controlled by a PWM signal. So what that means is pulse width modulation. You'll see on your Arduinos that they're along the digital pins, it'll have a section, it'll say PWM, and it'll have a little tilde next to it. So any of the pins on your Arduino board that have a little tilde next to them are PWM enabled pins. And these are the pins that we use to drive motors. And these are the pins that we use to drive servos, well, as they are a motor as well. So we can vary the pulse width, and that actually decides the position of the servo. So it's not actually that we give it a voltage or whatever. It's exactly tuned to the system because of the way servos are built and because of the way the control system works inside of them. So yeah, it uses this to force a DC motor to the correct angle, and it will keep it at that angle. So if you try to turn that thing, it will go back to it, and it will do everything it can to hold at its angle that you set it to. So yeah, this is the way I recommend setting it up. I believe that's a PWM signal pin 9. So brown is ground, red is 5 volts, and yellow is signal. I believe the ones we have, it's actually an orange wire for the signal pin, and we've got a red and a brown one for voltage and ground. But yeah, to make sure that you actually do give these things 5 volts. They will not run at 9 volts straight from the battery. It's not only that you will probably damage the motor, it's that it will straight up not work at all because it is expecting that 5 volts, and it's expecting the PWM signal to be related and sort of match that 5 volt expectation. So again, we have beautiful example code that is really useful built into the microcontrollers IDE for Arduino. So important parts is the myservo. We create an object and then we attach that object to a pin. It's kind of like setting the pin mode, but in the servo world, and having it go, okay, pin 9 is my servo object. And then you can just use it as if it's an object. So this is a much more object-oriented way to approach the problem, but it's a pretty nice way to do it, in my opinion. But yeah, so all this program is doing is it's essentially going, okay, well, my initial position is 0, and while it's less than or equal to 180, increase that position. So it's going to really slowly increase its position because it's, well, I say slowly, this loop runs a lot of times per second, but it's going to increase its way all the way to 180. And then for the next bit, once it's done and it's reached its final position, it sweeps it all the way back. Obviously, you can simply use the function that's just go myservo.writePos, because myservo is the object we've made. And so it's whatever you've called your object .write, and you simply just write a degree position into it. So if it's at 0 and then you want it to go up by about 90, you would put in 90 and it will simply move up to that position. And if you want to change it again, then you have to tell it to go to the specific spot that it needs it to be at. So yeah, I'll show again that this is all easy to find in here. So if you want this sweep program and you want to have a look through it yourself as well, it's in the Ooh, it's servo. Here we go. So in the examples for any board, I have it. I hope everyone has it. But yes, so for sweep, this is the exact program that is basically in the slide. It's straight from examples of the Arduino IDE. So yeah, and that's most of what you probably need to know for these things. If you have any other more questions, we're happy to help, of course. But that's the basics of setting these up and starting to use them in the Micromelon IDE. In the in the Arduino IDE. Yes. Okay. Cool.